All right, today we are diving deep into the absolutely fiery journey of one of our most essential metals. We're going to see how a dull, unassuming piece of rock gets crushed, melted, and zapped by electricity to become the gleaming, pure copper that literally powers our world.
So here's the game plan. First, we're going to meet copper and its famous relatives on the periodic table. Then we'll follow its incredible path from raw ore through a crazy hot furnace all the way to its final super pure state. And to wrap things up, we'll check out some of its surprisingly colorful chemical reactions. Let's get into it. So first up, let's meet the star of our show. What exactly is copper? Well, it's way more than just another metal. It's part of this small, exclusive club of elements that has literally shaped human history for thousands of years.
So check this out. Copper, along with silver and gold, they all hang out together in a special spot on the periodic table. And for thousands of years, these three have been known as the coinage metals. Why? Well, it's pretty simple. They were the foundation of currency. They don't rust or corrode easily, and they have this inherent value, which made them the perfect choice for making money.
But what really makes these metals tick? Well, beyond just being shiny and valuable, they've got some amazing properties. They're incredible conductors of heat and electricity, and that right there is copper's modern superpower. You can also hammer them into thin sheets or stretch them into wires, no problem. But honestly, their chemical behavior is what's really fascinating. Copper can exist in different ionic states, which is the secret behind all the vibrant, colorful compounds it loves to form.
Okay, so you don't just, find pure copper nuggets lying all over the place. It's locked away deep in the Earth's crust inside these minerals we call ores. The big one, the most important one, is copper pyrite, but it's also found in these absolutely beautiful forms like the stunning green malachite and the deep, rich blue of azurite. Our entire journey today starts with one goal: freeing the copper from these rocks.
All right, so how in the world do we get that copper out? Well, the very first step, even before we bring in the fire, is all about prep work. We have to separate the valuable bits of mineral from all the worthless rock they're stuck to.
This is the entire industrial process, the whole shebang, in 5 key stages. Think of it like a multi-step purification gauntlet. We start by crushing the ore, then we concentrate it. After that comes roasting, smelting, bezimerization, and finally the ultimate step, refining.
Now, after crushing the ore into a fine powder, this is where things get really clever. It's a process called froth flotation, and honestly, it's kind of like giving the ore a bubble bath. You mix the powder with water and pine oil, and then you blast air through the whole mixture. The pine oil is sticky, but it only sticks to the copper particles, making them float to the top in a bubbly froth. Meanwhile, all the useless rock, or gangue, gets waterlogged and sinks. It's a brilliantly simple and super effective way to concentrate the copper before things get hot.
Okay, buckle up, because now we're heading into the heart of it all, the fiery gauntlet. This is a series of high-temperature processes designed to systematically strip away absolutely everything that isn't copper.
Welcome to the smelting furnace. This is where we really turn up the heat. The concentrated ore gets mixed with silica, which is basically just sand, and a carbon source called coke. Then it's all heated to a blistering 1200 degrees Celsius. Everything melts, and it separates into 2 liquid layers. The heavy stuff on the bottom, that's what we want. It's a molten mix of copper and iron sulfides that we call copper matte.
But wait, what about all that other gunk we don't want? Well, this is where that silica we added comes into play. It reacts with the unwanted iron oxide to form this glassy liquid called slag. And here's the cool part. Since the slag is lighter than the molten copper matte, it conveniently floats right on top where it can just be skimmed off. It's a fantastic piece of chemistry.
All right, now for what is maybe the most dramatic step in the whole process. The molten copper matte gets poured into this pear-shaped furnace called a Bessemer converter. Then a massive blast of hot air is forced right through the liquid. This triggers an incredible chain reaction. The sulfur burns away as a gas, any leftover iron forms more slag, and the copper compounds, they basically purify themselves, leaving behind almost pure molten copper.
And as this super hot molten copper starts to cool down, all that trapped sulfur dioxide gas has to go somewhere, right? It bubbles out just like the fizz from a can of soda. And those escaping gas bubbles leave behind this rough, kind of blistered texture on the surface of the solid metal. And that's exactly why it's called blister copper. At this point, it's already about 98% pure, which is amazing. But for modern electronics, it's still not quite good enough. So there we have it, 98% pure copper.
For most of human history, that would have been incredible. But for the high-tech wires and sensitive circuits of today, we have to get rid of that last 2% of impurities. Time for the final polish.
So for that final push to perfection, we turn to this really elegant process called electrolytic refining. We take our impure blister copper and make it the positive electrode, the anode. A super thin sheet of perfectly pure copper acts as the negative, the cathode. Then we just submerge both of them in a copper sulfate solution.
Now you flip the switch, and the magic of electrochemistry takes over. On one side, at the impure anode, copper atoms start to dissolve into the solution as positive ions. These ions then travel across the liquid to the pure cathode, where they plate themselves out as perfectly pure copper atoms. It's like they're teleporting from the dirty side to the clean side. And any other impurities, like tiny bits of silver or gold, they just fall to the bottom, forming a valuable sludge we call anode mud.
And the result of all this? An incredible 99.95% purity. That tiny fraction of a percent makes all the difference. See, that level of purity is what makes copper such a perfect conductor. Even the tiniest impurities can mess up the flow of electrons, which reduces conductivity and creates heat. For our electrical world, this level of purity isn't just nice to have, it's absolutely essential.
Okay, so we've got our super pure metal. Now let's have some fun and explore its chemical personality. Because copper isn't boring and inert like gold. It loves to react. And when it does, it puts on a spectacular show of color.
You've definitely seen this reaction in real life, even if you didn't know it. Think about any old copper roof, or, you guessed it, the Statue of Liberty. Over years and years, copper slowly reacts with the water, carbon dioxide, and oxygen in the air. This forms that beautiful, protective green layer we call a patina. That iconic green color? It's a compound called basic copper carbonate.
Copper can also put on a pretty dramatic show. Take what happens when you mix it with nitric acid. Depending on how concentrated the acid is, you get a completely different result. A strong concentrated acid gives off these thick, brown fumes of nitrogen dioxide. But a dilute acid produces a colorless gas that only then turns brown when it hits the air. These visual clues are telling you exactly what kind of chemistry is happening.
You know, a solution of copper ions is basically a chemical chameleon. It's amazing. If you add some sodium hydroxide, poof, you get this pale blue solid. But if you add a bit of ammonia, the whole solution turns this stunning, deep royal blue. Every different chemical you add produces a unique color. It's like a chemical fingerprint that shows you exactly what's going on at the molecular level. And all these cool chemical properties aren't just for show. They lead to some really important real-world uses that go way beyond just wires. Copper sulfate, also known as blue vitriol, is a key ingredient in fungicides that farmers use. Cuprous oxide is what gives glass that beautiful, rich red color. And anhydrous copper sulfate is a neat little chemical test. It's normally white, but it turns blue as soon as it detects any moisture.
So let's just take a second to appreciate that journey. We started with a chunk of rock, a humble mineral locked away in the earth. We followed it through this intense, fiery gauntlet of purification and watched it become the 99.95% pure metal that underpins our entire technological world. Pretty incredible.
It really makes you wonder, doesn't it? We've seen how copper's vibrant color changes are like a secret code to its chemistry, and it leaves me with this one last thought for you. What other elements, all around us, are hiding their own fascinating secrets, just waiting to be revealed right there in plain sight?